Hello, today we're going to talk about the structure sheaf of an affine scheme, and we'll do a recap what it is, and we'll show that it's actually a sheaf. So let's take X to be the spectrum of a ring, and OX is going to be a sheaf on the following basis, namely the basis D of F for F in the ring, so the principal open subsets, and we've already seen in the last video that it's equivalent to define it on a basis or to define it on the whole space. So we'll define it on the basis at first. And we'll define it as the following localization. Also, let me give you a short note. So if we have D of F is actually equal to D of G, then there's a unique isomorphism from a F inverse to a G inverse. So that's just by the universal property. So, but yeah, that's a short reminder. And so what we are going to prove today is that OX is a sheaf. And well, at first we define it on a basis, but we've seen that with the construction from the last video, we can extend it to X, and then we get a sheaf there. So let's prove it. So we have to prove the two sheaf axioms. So let's take some principal open set and let's cover it by some other principal open sets. And now let's make some observation first. So we have the map which is induced by localization, namely from the spectrum of here to D of F. So this is a subset of the spectrum of A, and it's actually a homeomorphism onto D of F. And principal open subset correspond to principal opens. So that's actually nice, because what that gives us is that we can assume that so we have the D of F is homeomorphic to the spectrum of a ring. So it's now some other ring, but as we'll show it for an arbitrary ring, that's not that bad. So we assume, without loss of generality, that D of F is equal to D of 1, which is just the spectrum of A. So this is X. So we assume that, and then we have a cover of. So it's enough to show this for a cover of the whole space. And also let's make another remark. So since X is quasi-compact, we can assume that I is finite, so the index set is finite. I'll tell you a little bit more about that later. So for the first sheaf axiom, it's straightforward that we can assume it. For the second one, it's also not that hard, but it's not as immediate as for the first one. So let's start with the first sheaf axiom. So for the first sheaf axiom, we're going to show that if we have S in this OX of X, which is just, we've seen that this is, so maybe I should have written this OI. Yeah. So here that this is just A, and so maybe I should have written it here. So D of 1 is isomorphic to the spectrum of A localized at 1, but that's just A. Okay, so if we have such an S with S restricted to D of Fi 0 for all I in I, then S is 0. So what we've, in the definition, we had it with S and T equal, but as we have rings, we can actually assume that T is 0. Or not T, but so the restrictions of T are 0. So we're gonna show that. And now let me tell you why we can assume that this index set is finite. So if the index set wasn't finite, then we just, so all we have to do is look at these finite ones, and these finite ones already imply that it's 0. So the other ones we would have left out wouldn't change anything. So here that's clear that we can assume that the index set is finite, and I'll tell you later a little bit more about it in the case of the second Sheath axiom. Okay, so now let's start. So for all I in this finite index set now, there exist restriction maps. So namely from OX X, which is A, to OX D of F of I, which is this ring here. And this is actually given by localization. So if you check how we constructed the restriction maps, this map is given by localization. And that's important now because this tells us that S restricted to dfi is 0 is equivalent to that there exists an ni, so a positive integer or non-negative integer, such that fi to the ni times s is 0. So this is for all I. And now we take the maximum, so of these ni's. The index set is finite, so that's fine. We use that d of fi is equal to the principal open set of fi to the n. So that's, why is that? So that's because fi is in a prime ideal if and only if fi to the n is in the prime ideal. And now we have this, and we can, or let's put the n's here, exactly. And now we can show, so these are some properties of the Zariski topology and some set theory. So this is equivalent to the vanishing of the set of the fi to the n's being the empty set. And we've already seen in another video that this implies that we can write 1 as a linear combination of these fi to the n. So for some bi in the ring A. And well, that just means that S is equal to S times 1. But this is the sum over the bi and then fi to the n s. And now fi to the n s is 0 because this n is at least ni, and so this is 0. So we've proven the first sheaf axiom, so let's continue with the second one. So for the second one, let me first note why we can assume that the index set is finite. So if we have some g, where let's say g was in the possibly infinite index set, but isn't in the finite one we have chosen. So assume we have, so we glue together the finitely many elements to an element on the ring A, so on Ox of x, and then let me write it at first out. So this is just the union over the I and then g times fi, and now we get so if we restrict the set this element, so we started with si, we got some s, and these si were for I and I, and we got some s, then we can restrict s to d of g times fi, get some elements there, and now we can glue them again together on d of g because we have this finite union here, and so we get that this section S also, so let's say S restricted to d of g is equal to some, let's call it SG, which we prescribed before. And so it's enough to show it for a finite index set. Okay, but now let's prove it. So let's take Si in Ox of d of fi, and of course they should agree on the intersections. So we have these, that this should be equal to Sj if we restrict to the intersection. Oops. Okay, and this, of course, should be for all ij. And what we have to show is that there exists a global section, so as in Ox of x, which is equal to a, such that S restricted to d of fi is equal to Si. So this again for all I in our finite index set. So let's write Si, so that's what we need to show. So let's write Si to be Ai over fi to the n in the localization, and n independent of I, we can do that because I is finite, and if necessary we put some fi's in the numerator. Okay, so we have that Si is equal to Sj, which is Aj over Fj to the n, and of course if we restrict to the intersection, and restricting to the intersection means in here. So actually this would be a Fi inverse localized Fj inverse, but we can immediately see it by, I think I've written it here, yes. So this d of Fi intersection Fj is d of Fi times Fj, so we get this localization here. And they are canonically isomorphic, or at least there's a unique isomorphism. Okay, so that's that, and now we get by just the definition of localization that there exists a non-negative integer, so we call it m, which is independent of ij, because again the index set is finite, so if necessary we make it bigger, so such that fi fj to the m times, and now we have fj to the n ai minus fi to the n aj, and this is 0, and of course this equation holds in the ring A. And now let's write it out. So we have fj to the n plus m ai fi to the m minus fi to the n plus m aj fj to the m. So that's 0. And now let's have a closer look. So if we, or let me tell it at first. So instead of ai, we consider ai fi to the m, and instead of m, n, we consider n plus m. So we replace ai by fi to the m ai, and n by n plus m. So let's see, if we replace it, we get here ai. So let me write it here. So we would have ai fi to the m divided by fi to the n plus m. So that's the same. So we don't change our element, and also this equation so would still hold, because well, this we just have a bigger n. So that's still 0. Okay, but now we get from this equation that fj to the n ai is equal to fi to the n aj, and of course for all ij and I. And so what we will use now is that, as in the proof of 1, we will write these. So again, we have so we still have, let me see. So in 1, to write 1 as this linear combination of the fi to the n, all we used was that we have this open cover of x. Okay, so we still have the open cover, so we can still do this, and we let S be the following. So we define it to be the sum of bj, aj. And now let's see what this gives us. So we multiply S with fi to the n. So this gives us sum bj, aj. Exactly, that's S, fi to the n. Okay, now we take parentheses and we get that this is the sum bj, fj to the n, ai. So by using this relation, and the sum bj, fj to the n is 1, and we can put ai just in front, so we can write it like this. So we get that this is ai. And what does this give us? So, well, let's look at S in the localization. So what we get is that in the localization we have now that ai divided by fi to the n is S, and, or let's call it maybe not S, let's call it S restricted to t of fi, because it's not the same element, and that's what we wanted to show. So this S, so let me tell you, so we have the map from A to A, F inverse or Fi inverse, and S gets mapped to the element in the localization, so S at dfi. And by this relation here, we get that it's ai divided by fi to the n, but that's exactly Si. So that's what we wanted to prove. And we finally shown that it's a sheaf. Okay, so far for the structure sheaf. We still have to do a little bit more about sheaf theory, so we need to define the stalk. We want to know what the stalk of the structure sheaf is. We want to know what exactness for a sheaf means. So if we have some sequence of sheaves, we want to know what exactness means. And maybe some more stuff. Let's see. So these are some things we're gonna see in the next videos, but let's see how we'll go from here. So thanks for watching. Have a good day. Bye.